I know you're
Okay, so were there any from the 4.3 problems that we should talk about? So 4.3 is kind of stuff from last week. More practice with that. There'll be more on the quiz on Friday related to those kinds of things. So curve sketching, given the sketch of the derivative, could you sketch the original function? Given the accumulation function, could you sketch the rate of change? Etc. So that kind of stuff will be on the quiz. All right, so we want to talk about 4.4?
Yes.
Okay, so what was the first question? 10A? 10A. Good to go okay? Worth talking about? All right, next one. Shipping crates, 13. Yes, meaning let's talk about it? Okay, let's talk about that one. Okay, is this it? It's supposed to have a volume of 16 foot cubed, and the material for the base costs twice as much as the material for the sides, and the material for the top is half as much as the sides. So what are the dimensions of the crate that minimize the cost of the materials? Okay, so we read this question, and so what are your thoughts about progressing towards a solution here? Adonijah.
First thing I think is just get rid of all the various sides, put them in unit of one thing, like the sides. You know what I mean? It's like you have an equation for the volume.
Okay.
You know what I mean? Like you have S is a side, and then 1/2 S is the floor, and 2S.
And what does S stand? What does S stand for? What quantity?
Cost per foot of the side.
Cost per foot. Okay. So he wants to have some constant that means like the cost per foot of the sides, and then the base would be twice of that, and the top would be half of that. Okay, because they didn't tell us what the cost was; they just gave us the relative values of the cost. Okay, so that's a good element of this. Connor, what were you going to say?
Oh, I was going to say because it's a square based.
Okay.
And the top and the bottom are going to both be squares.
Okay.
So that two of the dimensions are going to be the same.
Okay.
Therefore, you can just basically find the volume of the box is going to be, its height times a certain dimension squared. So
Okay.
It's going to be h times x squared.
All right. So yeah,
16.
having a square top and base allows us to eliminate one variable, one dimension, right? Because they're the same.
And then you can do, total cost is equal to I think it's 4s plus, wait. Never mind.
Okay.
I have
So
to look at
these are both important, kind of more specific details about the solving process. What about the big picture here? So when you read this, what's going to be the kind of the big picture of our solution? Adelaide.
We're going to be using surface area because we're using material.
Okay, it has to do with surface area.
But use the volume to find what the sides are on the right track.
Okay, so surface area is kind of it's kind of helps us to get what? What's really the overall goal here? Okay, so how are we going to find the minimum cost?
You multiply the cost of the certain panel by the surface area.
No, but I'm talking big picture here. How are we going to find minimum cost? What's going to be kind of the big picture of solving this problem?
Oh, you're going to want to create a function and you're going to find.
Sharon.
Reason.
So, say it in your own words.
We have to find an equation to find the equation, and then
What?
a cost
Okay.
equation that shows the calculates the cost,
Okay.
and then take the derivative in it, and then set the derivative to 0 to see if to find.
Right. Okay. So the goal in working through all these details and information is to make a cost function, because it's saying what are the dimensions that minimize the cost. So the cost function is going to be the centerpiece of this, and we can use calculus then to find minimum cost. Right. Okay. And so and then all these other things are going to be part of the journey. Okay. That's some that you guys are mentioning. All right. Okay. So. Picture is always good. And then what do we say about the dimensions of the base? It's a square. So we can call those the same. So we're keeping things as simple as we can. Those dimensions are the same. So we can say x is the width of the bottom in feet, h is the height. So what am I saying here? 16 equals x squared h. What's that about? Okay, yeah, that's our volume equation. And we know for a rectangular box, it's length times width times height. And so length times width times height here is x squared h equals 16. Okay, this is what Adonijah suggested, that we call the price of the side materials some square foot. I'm going to use K instead of S, but it doesn't matter. S would be fine too. Okay, so these are just some preliminaries, right? These are some preliminaries. So from here, we can do what will the cost of the bottom be. So the cost of the bottom, so then Adelaide was talking about surface area. So to get cost, it's going to be our area times cost for whatever side we're talking about. So the base is twice as much as the side, so there's our 2K, times the area will give us the total cost of the bottom, right? Cost of the sides, so that's just our K, and then each side is going to be x times h, and we have 4 of them. Let me redraw it here. So the bottom is x squared, and its cost is 2K. The sides, each side has a area of x times h. Those have a cost of k, and we have 4 of them. All right, then the top. Oh, and then here we're using our relationship of volume, then to write h as a function of x. Remember that was from our volume from the previous over here. This was using the volume restriction of 16. So now I can write h as x. Okay, cost of the top. Also, the area is also x squared, but its cost is half as much. It's k over 2. So we're ready to, what did we say the goal was? Cost function. So we can just call it, overall we'll call it C. So what's how are we going to find the cost function? We did all the hard work, now it's the easy part. How will we get that cost function? Yeah, I'll just add the bottom. This is all 4 sides, right? And then the top. So it's just going to be that, plus that, plus that. Okay, and so we've got that cost function. Here it is. And we want to find what? What's our goal? We're optimizing, so the maximum cost, right? We want to find the maximum cost. Minimum. Okay, so we find the minimum cost. So if this is something like this, who knows? I don't know what this is going to look like, but I'm just going to say that. So how can we use calculus to find this minimum cost? Lauren, how can we use calculus to find that minimum cost? Okay. And why does that work? So that's true. You take the derivative and set it equal to 0. But just as important is we always want to keep in mind, why does that work? Why does that find us potential minimum? I know Tyler knows. David.
The rate of change of the accumulation is 0.
Okay.
So that in this case it was decreasing, now it's going to be increasing.
Okay. All right. Yeah, so the rate of change is negative. The accumulation is decreasing. The rate of change is positive. It's increasing. So there must be that one point in between where the rate of change is 0. And what does rate of change of 0 mean? Accumulation stays steady for a moment, right? If the accumulation stays still for a moment, that's a potential low point. So here the accumulation is decreasing, 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 decreasing. Here it's increasing, increasing, increasing. So where the accumulation just stays, doesn't change for one moment, is going to be that potential area or point of minimum. Okay? So here's that work there. And so you get this right here. So this is the minimum cost. 64, the cube root of 64/5 is the minimum cost, right? Is that right? Corey, you said no? Stanley?
Isn't that the value of the side length of the minimum, where the cost is minimum?
So what value did we find here?
Or the height, rather?
Is it the height?
Or no, x. So that's the bottom of the...
So x is still x, right? So
Right.
defining your variables at the beginning and then keeping track, don't lose sight of what every quantity means. So x is still x, and so how can you explain what that number is, Stanley?
So if you plug that number of x into the cost function,
Okay.
it will give you the minimum. It will minimize that cost.
Okay?
Use that value of x.
And this quantity is telling us what? What number is that? Or kind of
Oh, it's length.
Yep.
Feet.
Yep. So it's the length of the base in feet. Are we guaranteed a minimum at this point?
Not necessarily.
All we know is that it's a critical point. All we know is that it makes the first derivative 0. So it could be max. It could be one of these rest stop things. How can we verify that it is indeed a minimum? There's a couple different ways. Beth? Second derivative, okay. So can we take the second derivative here? Second derivative is 4k. It'd be plus 128k over x cubed plus k. And what will the second derivative need to be for us to say, yes, indeed, this is a min? So what's the second derivative of the situation where we have minimum? Positive, negative, 0? Positive. Rate of change is increasing, becoming less negative and more positive, which gives us concave up. So at this x value, we don't have to do any more work than just to say, at that x value, is this positive? Can you say that for sure? Talia? How come?
All the parts are positive, and so is X.
Yeah, totally. X is positive. Everything in here is positive. So plug that x in, you're going to get a positive number. Therefore, second derivative positive means first derivative is? What's the first derivative doing if the second derivative is positive? Increasing. Increasing first derivative along with a 0 first derivative means the accumulation is pausing, has to be a minimum. Okay, we did that. So what was that number again? So how would we, and then, so what Stanley said, how would we find the minimum cost? Yep, so use your cost functions. The minimum cost will be the cost of okay, and then you could check this on graph and calculator. How could you handle the k? So if we want to check this on graph and calculator. So when you get this is going to still have k in it, right? Yeah, so that when you get that answer, it's still going to have k in it. So it's going to depend on what the cost of the sides are, okay? So if you want to use graph and calculator to check your answer, Connor?
I just said k equals.
Yeah, so you can just set k equal to 1 and make your graph of cost with k equal to 1 and verify that this x value is the place of minimum. Questions on the crates? The shipping crate problem. Yeah, Judith.
Did you have to find the cost? Because the last sentence just asks what are the dimensions of the
Yeah,
crate.
that's true.
So you didn't really have to go through all that?
Well, for this particular, but certainly that's a very important thing to know how to do. Yeah, but in terms of answering this specific question and getting points for the homework, you're correct. You just ask for the dimensions. Yeah. Other questions?
So the dimensions are cube root of 64 over 5. That's going to be x.
Okay, and how would you get h? Well, yeah, so remember we came up with this. So using that relationship from the volume, we can get h from x. Other questions about this one? Okay, what was next? $14. Walking and swimming. Okay, so that's the circular pond. Talk about that. Let's talk about that one. Okay, so obviously a good diagram is always key for these. So let's read it. Man wishes to get from the initial point on the shore with a radius of 1 to a point on the shore directly opposite. He plans to swim and then walk. So part A says he swims 2 miles per hour and walks 4 miles per hour. So he swims. So this would be the starting point here. And he swims 2 miles per hour. walks 4. So what are the minimum and maximum times for the trip? Okay, so big picture in terms of solving process. What's overall goal? What's going to be the overall kind of strategy here to solve this? Megan.
Isn't that the square of the sense is theta and the log of the sense is pi, so you just come up with a function for those two and then compare
So what kind of function do you want to make?
a rate function, right?
What's that?
A rate function.
A rate function. Okay, so the question is, what are the minimum and maximum times that it takes to get from D to C? So do you want to build a rate function? What's that? A function of time. Do you want a function of time? So that kind of, so when you use that language, it kind of implies that time is your input. Do you want time to be your input or your output? Output. Autumn. Function of distance with respect to time. So output is distance for input of time. Time with respect to distance. Okay? So the output is time for an input of which distance? D to E? Okay, the tough part is how do we get that distance from D to E?
Good question.
Yeah, that's kind of, because our independent variable, our input variable needs to be like what we have a hold of, right? And we can build this function that outputs are the kind of the focal quantity. So if that input quantity is something that's hard to calculate, then that might not be the best choice. So what's that? Distance from D to C. Is that changing? Yeah, that doesn't really, it's that input quantity has to be some changing quantity that gives us these different possibilities here, like this.
Theta.
Okay, what about theta? Connor.
Yeah, the whole thing is time function. What it needs to be is a composite of, well, what I did is I had the arc length, which would be theta. Let's see, the arc length would be the walking, so that would be the 4 miles per hour. The arc length, the total arc length divided by 4 miles per hour, added to the length of that chord DE divided by 2. So that would give you those two distances divided by the respective rates.
Okay, so let's just, you're kind of jumping ahead there. That's okay. So let's really make sure before we start we're sure about what our input and output of our central core function is going to be.
What I did is that you can find the equation to find the core DE and then make it I'm sorry.
You're still jumping in ahead to the details. I'm back at the beginning. What kind of function do we want to have? What's the input of the function and what's the output of the function? So it's all good. It's all good stuff. I just don't want to jump into the details without having a plan, right? So yeah, so if we want to minimize and maximize time, then our function's output should be time, okay? So we want a time function. Not a function of time, a time function, a time function that outputs time. Okay? What about, so input, so two things have been offered up, the distance DE and the angle theta. Is angle theta something that we can, if we change it, does it give us the different scenarios? Oops. Does changing theta give us the different scenarios that we want? is it something that's we don't have to calculate? We just know what it is. Yeah, it's that we talked briefly at the end of class. Theta is the same as what in terms of length? So if we use radians, then it's the same as the number of radius lengths of arc, right? So it's both the angle, and the number of radius lengths, or the number of these BC units wrapped on the arc. So that's really convenient because you can use that angle as relative arc length, number of radius lengths. Okay, so now we want to build this function. So Connor had some good ideas here. So the total time in general will be, so we'll call it time function. Time is a function of theta. So what will the overall structure of this function be? Just in the,
two separate lines.
okay, so the
So from D to E and E to C.
what about from D to E?
So it's
Distance?
distance over the radius.
Time for
Like the time it takes to travel. Right?
swimming plus? Yeah, so I'm really encouraging to really slow down. So you get into trouble and confusion if you jump into details too quickly. So do things and look at the big picture of things and work on things little by little. Okay, so now the time it takes to swim and the time it takes to walk. So maybe is one of those easier than the other that we can start with? So I think you were talking about how are we going to calculate time in general. How are we going to calculate time?
Well, it's the distance from D to E over the rate, which is 2 miles per hour.
So dE over 2 miles per hour. Okay. Plus EC. So over 4. So distance over rate for swimming, distance over rate for walking. So what do we need? We need both of these distances. How? As expressions of theta. So if we can get dE in terms of theta, and we can get EC in terms of theta, then we got our time function. Okay. Either of those easier than the other? Is there one that we can start with that's easier? What's that? He said EC is equal to theta.
Yeah.
What is the radius of our circle? 1 mile. So if theta is the number of radius lengths and our radius is 1 mile, then theta is also number of miles, right? It's also the number of miles. If a radius is 1 mile, then that number of radius lengths is also in miles. So yep. So we're making progress here. So the question is, we need this in terms of theta. So how can we get this distance right here? What can we do? Anyone come up with anything to get that distance dE? What's that? Formula for a chord, okay.
2r sine theta over 2. In this case, theta would be 2 pi minus theta. In this case, you want to get the remaining angle in order to find the chord. So
Okay, so that's one way to go. You could do
Pi is theta.
this angle here is pi minus theta, and then you've got a formula for the chord as a function of radius. Okay, what if you didn't know that formula for the chord? Can we figure this out another way? The answer is yes. We can figure it out with some more just basic things that we know about circles and angles. Any ideas? And right triangles.
You got Pythagorean's theorem
Pythagorean theorem. Can we use Pythagorean theorem?
on a right triangle.
What right triangle? Can we use? Is there a right triangle we could?
Pi over 2.
You can write E, you can make E perpendicular to C.
Connor, what do you want to do?
Make a perpendicular segment between E and DC, and that way you now have
So now DE is our hypotenuse of this triangle here. And so DE squared what would it equal? Anybody? Dan, any ideas? Do you see the triangle that we're working with?
Yeah, could you make the right angle on the top instead? Or
What's that?
could you connect E to C and would that make the right angle?
You see the triangle that we're working with?
Yeah.
So Pythagorean theorem now doesn't involve angle. It involves, well, it will, but just involves side lengths, right?
Yeah.
So DE squared equals, so just in general, even if you don't know what these are, can you explain what this is going to look like, just in general?
From E to the diameter squared.
Right, okay, so let's call that, say that's our B, okay?
And that make that other line sort of like A or something.
From where to where?
From D to where the E meets.
Right. So now the question is, what are these? What is B?
it's R plus something.
Just sine theta squared.
Okay, he's offering up sine theta. Is that what B is? Sine theta. What do you think? Is it sine theta? Corey's got a big smile. You have no idea.
Yeah, it's the opposite of my
Sine theta, remember, Corey? Vertical distance above the horizontal diameter. Vertical distance
hypotenuse
above the horizontal diameter in radius lengths. That's what sine is. Is that B? That's exactly what B is. It's the vertical distance above the horizontal diameter in radius lengths. Boom. Okay, what about A? A is the cosine. From there to there is the cosine. Richard, agree with that? No clue. Daniel in the back. That whole thing from D to there is the cosine. Okay, what is the cosine of theta? If it's not from here to here, what is it?
cosine of theta would be it would be from B to the
From B to here.
right angle.
This would be cosine theta.
You just add that to R. Cosine of theta.
Yeah, so A is 1, which is the dB, plus cosine theta. Where's my? There it is. Okay, so I'm gonna have to rewrite some of this stuff. So our total time. Put it over here though. Total time is, as a function of theta, is our theta over, what was the walking again? 4? Plus dE over 2. And we said dE is? We said dE squared. Sine squared. Oops, you're right. This is squared here. Okay, so do you see an identity in here that's going to help us simplify this?
Sine squared plus.
Yeah, so if we multiply this out, 1 plus 2 cosine theta plus cosine squared theta.
Sine squared theta plus cosine squared theta equals 1.
Right, so you can see it right there. For a Pythagorean on this triangle, cosine squared plus sine squared equals 1. So those together equal 1, so we get 2 plus 2 cosine theta. Now, that's dE squared. So what's dE? So distance over time, distance over rate for swimming, distance over rate for walking. Anybody have a question? Does that make sense? Yeah.
You lost me back at how you got the 1
Great.
plus cosine theta squared.
That. So we want this distance here. So we're using the Pythagorean theorem on this triangle. D, let's call it, what do we want to call that point? F?
Sure.
So we want the Pythagorean theorem on triangle DFE. So DE squared is going to be DF squared plus FE squared. So FE is our sine theta. And what's DF? What's the distance from here to here? You see it?
Yeah.
Because
So
the
we
rate,
use
what?
the smaller triangle to get the cosine theta, and then you know it's one rigging like a plus.
Yeah, because this is our theta right here,
Okay.
right? That's our angle theta, and so we got the sine is the vertical height of that point, swept by theta, and the cosine is the horizontal distance from the center. But in our triangle, we want DF. So we got the cosine is that much, and then how much is BD? That's 1. 1 radius. Or, yeah, so, but 1 mile. So I did 1 plus cosine theta. Is it better?
Yeah.
And then sine squared theta,
Yeah?
you were saying that is equal to 1.
No. Sine squared plus cosine squared. That's an identity. From this blue triangle here, you see that it's also Pythagorean. Pythagorean identity is, so a squared plus b squared equals 1 squared. So cosine squared plus sine squared equals 1. So I'm gathering those two together. And that's 1. And then I added it to that one to get 2. Other questions? These are good questions. Gotta make sure we get this. Okay? So, we want to minimize and maximize the time. What does it mean? This is Daniel Herder. Want to minimize and maximize the time. How can we use calculus to do that?
We're going to take the derivative of the function.
Okay? No, so am I done with this derivative here? So I did 1 over 2 times the square root of that. Is it done? What else do I need? Chain rule, right? Chain rule times what? Which is what, Tyler? Okay, all you masters of derivatives. Right? Chain rule, right? Chain rule. 1/2, 1 over 2 times the square root of that thing, but then that's a function of theta, so by the chain rule, times the derivative of the interior function. Doing okay? Now what? So equal to 0. So since I'm setting equal to 0, I'll multiply both sides by 4. I'll get 1 plus -2 sine theta over square root of 2 plus 2 cosine theta. Check my math. Make sure I don't make any mistakes. Are we good? So I can move this to this side and then cross multiply, and I'm going to get Are we good? So I just moved this over and cross multiplied. And basically that just meant multiplying this up into the 1. Okay, now what? So the square root is causing problems, so we'll square both sides. Okay, so what we can do is we can change this to cosine squared, and we can form a quadratic of all cosines. So we'll have a cosine squared term, we'll have a cosine term, and we'll have constant. And then I'll make a quadratic of cosines. So sine squared is 1 minus cosine squared. Okay, so I'm going to have 4, so here's our quadratic, 4 cosine squared theta plus 2 cosine theta minus 2 equals 0. Divide by 2. Alright, does this factor nicely? If it does, that's good. If it doesn't, we'll just have to use quadratic formula. So does it? So 2, I'm just going to abbreviate cosine theta just as c theta. So I need a -1 and a +1, and I need to get +1 cosine. I think we're in good shape. What should this be? -1. I think that does it. Okay, so it's going to give us 2 angles. Cosine theta equals 1/2, and cosine theta equals -1. So what angle gives us a cosine of 1/2? Meaning this right here is half of BC. So let's kind of position that and see what angle. No, that's not what I wanted. Oh, this thing here. That's right. Okay, so I'm trying to put it at about cosine at about 1/2 of BC. Remember what angle that is? (60°), pi over 3. That's right. Okay, this one? Cosine theta equals -1. So where is this value from there to there? Negative 1. For what angle theta is your horizontal distance? Negative 1. 90? 180? Right, here. Theta equals pi. So what would be nice is one of those would be the minimum time and one of those would give the maximum time. Does it make sense that that's true for one of those? So pi over 3 is what I'm showing right now. Pi, theta equals pi means what scenario for the person? What's that? Walk the whole time. And don't do any swimming. So what could that possibly be, max or min? Probably minimum to walk the whole time? No, probably the maximum. That's probably the maximum time right there. Maximum time would probably be walking the whole time, or theta equals pi. Okay, and then it would be nice if this was our minimum, pi over 3. So how do we check that? How do we know what we've got? How can we check to see if we got maximum or minimum? Chelsea? Second derivative. Okay. How do you feel about that? Yeah, that is definitely the first thing we think of in terms of checking that. But let's bypass that and be a kind of be quotient rule with chain rule, and it's totally doable, right? It's very doable, but a lot of work. So what is something else we could do? How else could we use this equation, the first derivative equation, to check to see if this is minimum?
Value just below it.
Okay.
Just above it.
If we put in a theta just below pi over 3, and then one just above, what would we be looking for this to be minimum? If for the angle just before pi over 3, we'd expect this to be
Negative.
positive or negative?
Negative.
If we're expecting this to be minimum.
One before is going to be negative.
Before, time should be decreasing, meaning the first derivative is negative. And a little bit greater than pi over 3? Positive. Okay? So let's, so pi over 3 is a little bit greater than 1, right? So let's put 1 in. So in your calculator, so we can use graphing calculator. So we've got this expression, t of I'll call it theta is x. So what do we got? Actually, we're looking at the derivative of t. So what do we want to call that? Capital DT. And I need to make sure it's a string. There we go. Okay, so this is the derivative of our time function, and we said it's 0.25 plus negative 2 sine x divided by square root 2 plus 2 cosine x. Okay, and I'm checking, so pi over 3 is a number a little bit greater than 1, right? So for the number less, I can just put in 1. And what is it? Negative. So to the left of pi over 3, the time is decreasing. And then we could do 1.5. Also negative. Let's see.
Isn't the denominator supposed to have a 4? 4 times the square root?
Thank you. Yep. Thanks. All right, so let's try that again. 1 is positive. Do I have this wrong? Minus 2 sine minus 2 cosine x. What's? Yep, here's that's the minus I'm doing right there. 2 sine x over 4 times 2 plus 2 cosine x. Why is that positive?
That's negative.
What?
Is that not a negative value?
No, it's not. Well, maybe this is maximum, and this is minimum.
Well, he walks faster than he swims.
Right. So if we didn't make any mistakes, that's what this is seeming like here. It's seeming like this pi over 3 is for maximum total time, because a little bit less than that angle, the time is increasing. And a little bit greater than that angle, time is decreasing. So checking pi, so a little bit less, 3, negative, 3.15, positive. Yeah, so this seems to be the maximum angle for maximum time, and walking the whole way seems to be the angle for minimum time. Okay, so quiz on Friday and recitation will be like 4.3 homework, stuff from last week, and then of course you're going to have at least one of these types of problems. And then homework Friday will be some more practice of these. Okay. What happened? Yeah, there's a lot involved in that problem. Where did I lose you? Yeah. It's all, there's nothing in there that's we haven't covered, either in pre-calc or this class. It's all stuff we've done.
Why are we using physics and calculus? Come on. I only do it right with dry clothes. I walk the whole
Hey.
So what did you do?
I'm going to graph this original time function and see. But go ahead, ask your question.
Just in this algebra part for the what was it?
So I took so the derivative is okay?
Yeah.
Set it equal to 0. And then I just moved this over and cross multiplied, so just basically these are equal.
Right.
Squared both sides.
But to get rid of the
Get rid of the square root. So now I've got what I want to do is create a quadratic of all cosines. You got that?
Yeah.
So sine squared is 1 minus cosine squared. So
I
then,
see. Okay,
so sine squared is
that's what it's equal to.
yeah.
Okay.
And from that I can then make this quadratic of cosine. So I'm going to have oh yeah. So minus 4 is going to be plus 4 cosine squared over here, plus my 2 cosine, and then plus 2 minus 4.
Okay. Yeah.
Then I divided by 2. And then you can factor of cosines, and then you get the 2 different angles. So let's graph this and see if it's what we said. So now we want y equals t x. Sure enough, maximum around pi, or maximum around 1, pi over 3, and minimum at pi. Yeah, it works. Yep, there's a max 1.0472, which is pi over 3, and then minimum pi. Sweet.